Where was this one? The first. It's very light. I see.
के पास और फिर सुबह 6 बजे अच्छा उधर भी 3 बैट सब जगह 3 बैट
Not so easy to fit.
Job. Oh my god.
Yeah, whenever.
Yeah.
Yeah. Okay. Start the last of the program. Now Atul will speak on Launa traces with semi-marginal.
Thank you, Tulsi, for introducing me. Hello to all of you. First of all, a very big thanks to organizers, especially Julia and Yogesh, for organizing this workshop and asking me to speak. For most of the week, I was away, so I was unfortunately not able to attend any of the talks. So I regret for that. I'm sure they were great talks last week and this week. Okay, so this workshop has three main areas: complex analysis, convex geometry, and probability. Unfortunately, my talk will not have any convex geometry in it. The topic that I'm going to talk about is a mix of probability and complex analysis. So I thought this would be appropriate for today's audience. So the title is Existence and Simpleness of Loaner Traces with semi-martingale drivers. And this is based on a joint work with Yijing Yuan, who is a postdoc at Cambridge, and Vlad Margaret, who is a faculty at UNC Stockholm. So what I will do for this talk is I will straight away give you the problem statement. What does this title really mean? And what I'm proving. So I'll straight away give you the problem statement and then give you the motivation why I'm interested in that particular problem. Then present you the theorem statement, and if time permits, we will go a little bit into the details of the proof. So that's the outline. Okay, so let's start. So the problem starts as follows. So we start with a very simple object. So let W real valued. Okay, so R is just continuous real valued function, and let's say you are starting at 0. So this is the input of the Loaner theorem that I'm going to describe, and using this continuous driver, this is often called the driving function. Using this function, what we are going to do is we are going to generate a family of sets in upper half plane, which grows little bit point by point by adding a point at a time. So these are family of sets, compact sets in upper half plane, which grows by adding one point at a time. In such a way, so this growth is characterized in such a way that let's for simplicity, let's say the curve that you're growing is just a simple curve. This is a curve which is growing one point at a time. This need not be always the case, but I'm just taking a simple example. Now, this growth is prescribed in such a way that if you consider the complement domain, if you remove the curve from the plane, from the upper half plane, and consider the simply connected domain that is left, you can map it using a conformal map. So this is my, let's say, KT. This is the set which is growing. Okay, the complement can be mapped to back to the upper half plane. Now, the requirement relation to the W is that you want your tip, which is the point which is added at time t. You want that tip to get mapped to WT under that conformal map. So this is the Riemann uniformizing map, which maps this complement domain to this back to upper half plane. This is just Riemann mapping itself. So this is the requirement. You want, given any W, you want to construct a set of a family of sets such that this satisfies this property. That the tip, which is the extra point which is added to at time t, gets mapped to WT under the corresponding uniformizing map. Now, intuitively, you can imagine that what this map GT is doing. It is kind of, you imagine this is a zip, and it is unzipping the curve flat onto this real line. This is the intuitive picture that one can keep in mind. And you want this point to get mapped to the center of the zip. So this is a heuristic picture, but this can be made precise, and the way to make this precise is as follows. So what you do is, for each z in upper half plane, you consider the so-called lunar differential equation, which is as follows. So this is an equation which prescribes the growth of these conformal maps. So as your family grows, you consider a fixed point z, and as your family grows, you get a family of conformal maps prescribed by t, and this lunar differential equation prescribes the growth of that, which is exactly given by this differential equation. Starting from. So that is just saying that when your t is 0, you don't have any set. That means your GT is just the identity. Now, what will happen now? This differential equation, you can see it's 2 by whatever. This is in upper half plane because this is the real value. So imaginary part will be negative. And just do a little bit computation. So what this really says, that imaginary part of this conformal map GTZ, as time t grows, will keep on decreasing. So here's a picture. You had C, ZTZ imaginary part keeps on decreasing. Like that. And you have WT here, which is on the real line, which keeps on moving like that. And it may happen that the solution may catch the singularity, which is to say that this part will, at time as t approaches some value, it may happen that this blows up. And you call that time, blow up time, as Tz. Okay. And if you take the set T, Kt, which is all set in upper half plane, such that the solution GTZ catches the singularity before or equal to time t, that is exactly the family that we wanted to construct. It's a very easy to check that this KT, if you take KT to be this, then this is exactly the family of compact sets that we wanted to construct. We wanted to construct a family which has this property. If you take the mapping out GTZ, then the tip is mapped to WT. And this family exactly has that property. So this is called the lunar chain. Lunar chain driven by Now, the question that I'm very much interested in, and also it is very natural to ask, is how does this family look like? You have to begin with, a priori, you only know that it is some family of compact sets which grows in a particular way. But can we say something qualitative about this family? Now, in general, this can be a very wide object. It can be, so KT can be space filling. Something like, I don't know how to draw a space filling curve, but I will try. It can really fill the space as time t grows.
What is the driver in that case?
There are many. One particular case is 8, something like that. Okay, I'm not quite sure. Yeah, I will tell you later. There are some examples, but I have not set the stage yet to give the answer to that. Okay, so this can be a very wide object. So this is one particular example of very wide case. Another thing that can happen is that you may have a triangle like that, and you may have a logarithmic spiral. So you can start at the origin, and let's say, and you can, as time t grows, the KT can spiral around this triangle. So in the end, it becomes non-locally connected. So this a very wide object, something like a sine curve, topologist sine curve, something like that. Okay. So the question that I want to ask is,
KT space filling is TZ infinity. The
sorry,
if KT is a space filling curve,
yes.
then this TZ is infinity or
No, it says that every point is absorbed at some point. That says TZ is finite for all Z. That's what it is. So this is the, yeah, so KT is a set of all points which get absorbed so a set of all points says that the singularity is hit before time t. So space filling would mean that all points are hits a singularity in finite time. Okay, so these are some wild examples, but there are some nice situations as well. So a nice cases. KT is just a simple curve. For example, you have a curve like that, which is simple, just which grows in the upper half. This is the nicest possible case that you could have. What you could also have is a curve which is not necessarily simple, but it does intersect itself. Something like that. So this is also a relatively nicer case as compared to being a space filling or non-locally connected. So what I'm interested in is in this question, under what conditions on the driving function WT you land in a nicer situation, not in the bad looking situation. And there's a way to formalize this. So this is the question of existence of trace. When does there exists a gamma, which is a curve in upper half plane, and this can also touch the real line. So I'm going to make it closed upper half plane value, such that KT, so H minus KT is unbounded component of equals to unbounded component of H minus gamma. The image of the two times. So this is exactly this picture. This is the way to formalize this picture. You have, or even this. This is even better. But what I'm asking is when can you construct a curve gamma such that the complement of the KT is exactly given by the unbounded component of the complement of the image of gamma. And if this happens, then we say that the trace exists. Okay, and in that case, the gamma is called the trace. Okay, and you can also prove that if this happens, then there is only a unique gamma that can satisfy this property, and in that case, you call that gamma to be the trace of the corresponding energy. Is the definition super clear? Now, answering this question in the full generality turns out to be a bit hard problem. I have certainly wasted too much time thinking about it. So in full generality, this is an extremely hard problem. I can say that. But what for this talk, what I would do, I would restrict my attention to a simple case, a particular case. What I do is I choose W to be a sample path of a semi-martingale. That is to say that WT is given by some martingale plus some bounded variation, both continuous. So both M and A are continuous. This is a martingale, this is a bounded variation process. Now, using martingale representation theorem, assuming that your filtration is rich enough to support a Brownian motion, you can write it as a stochastic integral. This is a Brownian motion with some diffusivity, kappa, which can be random, not necessarily constant, some adapted process kappa. Now, what I asked in this talk is, suppose I take my W to be this, can I answer this question? Can I say that gamma exists or not? And can I say some quantity, whether this or this picture happens? Okay, whether it is simple or a picture like that. So this is the problem that I want to address in this talk. Now, before giving you the answer to that question, let me give you a motivation. Why am I really interested in posing, or why it is interesting to take this W to be a semi-martingale of this particular form? Now, in order to understand that, we will have to look into a little bit of history of this subject. And this really started with the work of Oded Schramm, who was the first one to observe that it is really interesting to consider random drivers. And in his work, what he considered W to be some constant times the Brownian motion. So this particular case has a very interesting property. First, so there is a theorem which is due to Rode and Schramm. In this case, when your W is some constant time Brownian motion, if kappa is not equal to 8, then gamma exists, and it is simple for kappa less than equal to 4. Now, this particular case is interesting because it has a very nice property that the corresponding gamma that you get has two interesting features in it. One is called the domain Markov property, which is to say that if you grow a curve, okay, and remove it, then the remaining of the curve is actually has the kind of same distribution as the original one, except in a different domain, in a domain in which you have taken the curve out. There's something called domain Markov property. And the other feature is called the conformal invariance, which says that if you consider the law of such curve in upper half plane and map it to a different domain via conformal map, then the image will have the same property as the original. That's the conformal invariance property. And these two property actually translates into the fact that WT has independent and stationary increment, which is exactly the Brownian motion. Brownian motion is the only curve, except assuming continuity, which has the more or less the only curve which has the independent and stationary increment property.
So when you say it is simple for kappa less than equal to 4, the other way around, it is not simple.
It is not
It's known.
Yes. So this is if and only if. This is if. It is not simple for kappa larger than 4.
Any Markov and conformal invariance is for any kappa not equal to 8. Or
Sorry, can you say that again?
domain Markov property and conformal invariance is for all kappa.
Yes, for all kappa, yes. But this proof does not work for kappa equals to 8.
Okay.
There's some technicality which is very hard to explain here. Yeah, so this is where the story of random driving functions is started with the work of Schramm, and in which case they prove that such a gamma exists. It has some nice features, and these curves are exactly called SLEs. These are SLE defined to be Schramm-Lohner revolutions, SLE kappa. And these are important class of processes which appear as scaling limits of various 2D statistical mechanics models. So I will not go in that direction. I will not explain where does these SLEs appear, but that you can take my word for these are some important class of stochastic processes. Okay, so this is the case when you have driving function, which is a Brownian motion, constant time Brownian motion. But in this talk, which is the new thing, I'm considering a martingale, which is not necessarily, this kappa is not necessarily constant. Okay? If this kappa is constant, then you fall back to your original, the case of Rod and Schramm. But for me, what I'm interested in taking kappa to be non-constant and potentially random. Okay? Now, where does that appear, and why is that interesting? So that is interesting for this following reason. So let me erase this. The story of non-constant kappa starts with the work of Kumatu. So far, this theory that I've been developing, everything was done in a fixed ambient space, which was the upper half plane. Okay. So everything was with respect to upper half plane, which is a very nice, simply connected domain. Now, naturally, what you can ask is there a variant of this theory in finitely connected domains? So a domain of this form where you kind of take out some loops out and understand the growth of curve in that domain. A very prototypical finitely connected domain is called a standard slit domain. In which you have the upper half plane, but what you do, you take out some horizontal line segments away from, out from the upper half plane. So a natural question is, can you develop the theory Lohner differential equation and related things in this ambient space where you don't have the simply connectedness property? Now, the advantage of having a simply connected domain is the Riemann uniformization theorem, which says that you can map every simply connected domain to each other. So that kind of theorem does not really work in full generality to such finitely connected domain. But you do what you have. What you do have is some kind of generalizations, which says that two domains can be mapped to each other via conformal maps, which if and only if they have the same type. Now, right now, I'm very loose in saying what does type mean. But as an example, you can consider the case of annulus. Two annuluses can be mapped to each other if and only if the ratio of their inner and outer circle are the same. So there's a theory, well-developed theory, which gives you the generalizations of Riemann uniformization theorem for finitely connected domains. Now, so now let's consider a finitely connected domain of this type. Okay, and in this domain, I'm going to grow a curve like that and take it out. So I have a domain H tilde, which is a finitely connected domain, and I'm going to take it out, take the curve out from this. Then this can be mapped to via conformal maps to a fixed finitely connected domain, again of the same type, and this we call it as dt. And the corresponding variant of the Lohner differential equation is what is called the Komatsu equation, which is of this form. Psi dt now recall in the previous case what the right hand side was GTZ minus WT. This I'm going to write it as psi naught GTZ WT, where psi ZA is just 1 by Z minus A. Now this thing is nothing but a complex. So if you take the imaginary part of this, this is nothing but the Poisson kernel. If you take the imaginary part of this thing, so this is a complexified Poisson kernel, which appears in the Lohner theory in the original case. And similarly, in the Komatsu equation case as well, again you have some kind of a kernel. Now this is this is not explicit at all. You cannot write a closed form formula for that, but there is some kernel, nice enough kernel psi dt, such that the growth of the corresponding conformal map can be given by the right hand side is given by that. So instead of 1 by Z minus A, you have something else. So this was the work of Komatsu in 1950s. But then there was later work by then Fukushima, which really established this in full great detail. So there were some gaps in the early work of Komatsu, but those gaps were completed by Chen, Fukushima, and Roth, and they established this Komatsu equation, Komatsu differential equation. Now, having this generalization of Lohner theory in finitely connected domain, you can again ask what are the curves, but which has the property of domain Markov property and conformal invariance. Can I find a curve which has that corresponding property of domain Markov and conformal invariance? And this was established by so this is the work of Chen and Fukushima in 2015. It said that if gamma has no, so to begin with, I don't really know. I'm too strong. So to begin with, I don't really know whether gamma exists, but I'm assuming for now that there is a nice gamma. So Chen and Fukushima they showed that if gamma has domain Markov property plus conformal invariance, then WT has to have a nice formula. has to come out of some nice object. Okay, I'm not going to write what that formula is because it is extremely complicated and it's not going to add any value for now. But the work is that if gamma has domain Markov property and conformal invariance, then WT has to be of some certain form. And then there was a full follow-up work, again by Suzuki. It says that in that case, gamma can be reparameterized so that this is equal in distribution, gamma is equal in distribution to a loaner chain driven by semi-Martin. So the case of loaner chain driven by semi-martingale actually is important because of this connection. If you consider the variants of SLE infinitely connected domain, they are nothing but reparameterized loaner chains driven by semi-martingale. So this is the connection. So this is my motivation to considering behind considering drivers of this form. And asking the question now, so far I have been kind of assuming that gamma exists, but that is not at all the case. That's the problem. That's the main problem at hand. Can you really say that gamma exists or not?
Okay, this local chain is without any slit.
Without any slit, yeah.
This is a normal.
Without, yeah, in the upper half plane, of course. Yes. Yeah. So the slit thing after reparameterization is same as original thing, but with a driving function which is different. Which is assignment.
When you do the mapping, you have these finite number of slits and you look at the different slits.
Yes, different slits.
And when you evolve,
Slits are also evolving.
Yeah. Are you assured that they don't have
They will not collide. Yeah. So this equation comes with a complementary set of equations which prescribes the evolution of the slits as well. And that equation is designed in such a way that does not allow these things to collide. Yes. Yeah. So now I'm going to back to the problem of considering this driver and trying to answer the question of existence of gamma.
And these things have been done with slit domains, not any other general domain.
Yes, yeah. In any other general domain, it's extremely difficult to write any kind of equation like that. They take this to be a prototypical finitely connected domain. There was some earlier work by Daping Zhan, which is annulus. So you can do a relatively simple, you can develop a relatively simple theory when you are doubly connected in the case of annulus. But the general case of finitely connected domain, that becomes complicated.
All finitely connected domains are like that, right?
It can be mapped to, yes. It can be mapped to, yes. Under conformal equivalence, it can be mapped to.
That really doesn't make sense, but this SL is going to where? I mean, to infinity or to one of these net points or
It is going to infinity. Yes.
it is like going to that one more.
Yes. One more boundary at infinity.
So you don't have to touch it to any point.
Yes, so it can touch. It depends on the driving function too. But so far, what I know is,
But then the process stops at
you stop at So theory is only developed for T small enough. It's not really developed for full time.
My question was like, in the annulus case, was the load to basically to go from inner to outer circle or within the same, so it is going in the same connect component of the boundary, right?
Right.
That's what you're saying.
No. So the work of and it was exactly this, except you just have doubly connected. Exactly. Yes. So. Okay, so coming back to that problem, now I'm going to try to answer this question. So the approach of verifying whether gamma exists or not is based on a condition you proved, which was already proven by Node and Sham, which is as follows. So gamma. So this is an if and only if condition on the existence of gamma. So the gamma exists if and only if this condition X. You can. I'm going to explain what these terms are. And continuous in T. So here my Ft is the inverse map of GTC, which takes upper half plane back to complement domain of KT. And here is your upper half plane. WT is here. This is the tangents, non-tangential. So this IY only one coming from the vertical direction. This is important because we are taking the non-tangential limit. So if you can verify that the non-tangential limit exists of this conformal map as you approach this boundary point WT, and if furthermore if you can verify that the corresponding limit that you get preserves the continuity in time t variable, if these two conditions are satisfied, then you can show that this gamma exists. And this actually, the gamma t is exactly given by that limit. The trace exists if and only these two conditions are verified. Now, in particular, these two conditions can be verified from this estimate. So the above follows. This follows. If you can verify a different estimate on the derivative of the conformal map, the theta is a parameter less than 1, strictly less than 1. And for y, let's say y is smaller. If I can show that the derivative of this conformal maps decays like that, y to the power minus theta, where theta is less than 1, then just using the fact that this is integrable for theta less than 1, that already says that Ft has to be Cauchy in Iy variable. And that shows that the limit must exist. And if you have the uniform estimate in supremum, that also gives you the continuity in the time value. So both these conditions can be verified by proving this auxiliary estimate of this form. Now the heart of the matter is really establishing this estimate, which is the kind of the difficult part of the proof. Now, how do you really how do you prove such things? So in the original work of Rode and Schramm, the way they did this estimate was using this backward lunar flow. And this is a very simple observation, which is as follows. So if you have a point Z in a path plane, and if you have Ft, which maps it to some complement domain, this is going to be. Now, if I start my GT, like GS, from this, starting at this point, then at time t, I'm going to get mapped to Z. Right? If I consider as my, so if you start your this flow, GS of FTZ, at S equals to 0, you are here, but at S equals to T, you are at Z, because they are FT is the GT inverse by constructions. So if you want to understand what FT is, you take the reverse of that reverse ODE, starting from in the backward time, and by solving that ODE, you can extract the information about FTs. So this is the point of this lemma, which says that if you consider EHS starting from IY, then HT of IY, so is exactly HT of IY. Now, so what this is really saying is that you can find this value by solving this equation, where US is the reversal, time reversal of the driving function. So because you are flowing in the backward direction, this is the reversed ODE. Now, so this technique works well when you have Brownian motion, because the time reversal of Brownian motion is again a Brownian motion. So there is no problem with that. But if you are interested in understanding semi-martingale drivers, time reversal of semi-martingale is not always a semi-martingale. That is not at all the case. There are some cases, e.g. diffusion, if your semi-martingale is coming out of the solution of some stochastic differential equation, then you can say something about the time reversal. There is a very nice technique of expansion of filtration. Which says that if you have let's say a semi-martingale, and suppose if you expand the filtration by adding some extra information, you preserve the semi-martingale property. And there are some good results in that direction, but the punchline is that not all semi-martingales have that property. Not every expanded filtration preserves the semi-martingale property. So this technique of using the backward lunar flow does work for Brownian motion, but it fails to apply for to general semi-martingale because you do not really have the time reversibility property.
Can you get some probabilistic representation of this?
Which one?
That HT, I mean, is backward. I mean,
yes. So this is exactly the. You mean to say, can I solve it explicitly? When you your Brownian motion, when your H0 is real valued, this is exactly the Bessel flow, Bessel equation. But started from complex plane, it is some process. You don't really have a closed form.
I really missed it, but when you're considering WT to be random, the supremum bound, do you need it?
Almost sure.
Almost sure.
Yes.
Okay.
Yes, almost. Okay, so this use the technique of trick of using the backward lunar flow does not really work for semi-martingale property. It's a semi-martingale driver, but so WT is semi-martingale. So WT has semi-martingale property, which is driving the flow of GTC. Okay. So GP, the growth of GTC is being prescribed by this equation. And W has a semi-martingale property. So this is the forward equation. Should have said it. So there's +2 here. Here there's -2 because of the time reverse. Okay, so the probabilistic. Yeah. So because we only know the semi-martingale property of WT, we can only analyze GTC. We cannot analyze the inverse of. Yeah. So we cannot analyze the backward flow. We can only analyze the forward. So the idea is as follows. So we kind of use the so to estimate T prime I y plus WT, we use the very simple fact which is um, is that correct? I often do it wrong. That's correct, yeah. We just use this very simple fact that the derivative of the function is actually the inverse of the derivative of GT, but evaluated at a different way. The goal is to estimate that. We can only estimate GT prime because we only know the information about forward flow. But again, you are left with this Z, which you don't have any information about. So the idea is as follows. So what you do is estimate GT prime for sufficiently many Z, okay, which will proxy for this quantity. If I have, let's say, I a priori know that this FT of prime of IY is going to be located in some box. There's very a priori bound. There are many a priori bound that you can prove regarding this object FT prime, which actually says that FT has to be in some certain box. Okay. Now, because this is a random object, you don't really know where it is. Okay. So what you do is you kind of postulate a proxy for this object. So what you do is you find enough grids. Okay. And estimate GT prime of Z for each of these corner points. Now, if I can do that, then I can estimate this no matter what this object is. So this really boils down to first ingredient in the proof is that suppose I can control GT prime of Z, then can I control GT prime of W, where W and Z are close enough in some sense. I don't really know what this close enough means. And this actually this can be done by using what are called the distortion theorems. Therems, which in the circular this version it just says if you have a univalent map, then this can be bounded by something like that. So just Google Convex distortion theorem. You will find this estimate of this one. Now, this theorem really allows us to control G prime at any point from the information about G prime of the information of G prime on these points of the grid. So in order to estimate FT prime, what we do is we estimate. Also, there is a minus one. Okay? So then, if you want an upper bound on that, what you really want is a lower bound on the mod of G prime. So as the problem of estimating this can be boiled down to estimating of GT prime for sufficiently many Z. Now, understanding the correlations of GT prime for different Z again turns out to be a hard problem. But what you do in the end is just do the union bound. So in the end, you want to apply some Boyle-Cantelli argument, where understanding the correlation for different Z is a bit difficult, but you simply apply the union bound. So estimating GT prime Z for sufficiently many Z can be boiled to any good moments. Now this is negative moments. So what we are interested in is in the lower bound. So what we really need is negative moments. Estimate where lambda is a negative one. So if I can estimate this, then using applying Boyle-Cantelli and union bound, I can estimate that, and using that, I can estimate this. This is the line of argument. So everything boils down to having this estimate. Now, just using the fact that GTZ satisfies this differential equation, where WT is a semi-martingale. Okay, so let's first consider the case when WT was a Brownian. If WT is a Brownian motion, what you can do is actually you can use the Feynman-Kac connection to write a PDE for that. So in fact, GT prime of Z can be written as the part of this GT Z minus WT whole square. So if I raise it to the power lambda, I have a lambda here. If I want to compute expected value of this is the same as computing expected value of certain functionals of GTZ, where GTZ is coming out of a solution of this equation. Now you can use Feynman-Kac connection so this essentially says that this expected value solves a PD, some PD. You can actually differentiate with respect to time and differentiate with respect to Z, and there are some connections between the time derivative and the space derivative.
And these both the equations are first order equations, so there is no presence of any second order term.
No, PD will be second order. The Feynman connection, FK, yes.
Here,
Here it is first.
The backward as well as forward.
Yeah, it's yeah. So the order, in the terms of order, it's not complicated. It is complicated because of the. So these things are complex value. So there is imaginary real part and imaginary part, and they are coupled together. This is where the difficulty is. Yeah, otherwise there is no difficulty. So I was saying that you can use Feynman connection to obtain a PDE for this expected value. Now, whether you can solve that PDE or not is a different matter altogether. In fact, it's not in this particular form. You cannot really solve it explicitly. But what turns out to be the case is if instead of value of sorry, if you consider kind of weighted expected value, weighted mean, weighted moment, which is given by imaginary part of GPC, some power psi, and I think that's it. Other part is not important. If you instead of considering this, I consider a different example, a slightly similar looking, but also different. I have put a weight which is imaginary part raised to some power. And it turns out that if you write the corresponding Feynman-Cat PD for this this expression, then that PD can be solved explicitly.
But there is a PD for G prime, right?
It is a PD for, what do you mean by that?
So that connection, Feynman-Cat, that form.
GT prime is given by that. It's a functional of G original GT.
So then when you have the solution of the Feynman-Cat expectation,
Yes.
so that's that PD is for G prime or G.
G prime.
Yes, that's what.
It's a PD in Z and T value. There is no G prime. The expected value. So GTZ comes out of this equation. W is the Brownian motion.
Now you are doing with the G prime equation, right? And from here you are relating it with the Feynman-Cat formula and getting a solution of the equation with the expectation. So this PD
Yes.
is of G prime.
It's a PD in Z and T variable. There is no G prime.
So that expectation of G prime will come as a solution of that PD. Right?
No. See, that's why when you take expected value, this guy averages out. This is where the PD comes. PD comes from the fact that Laplacian Brownian motion has generator, blah blah blah. This is where it comes. There is no G prime there. It's just a PD in Z and T value. That's it. So the point I was trying to make is that this is all a bit vague. It is a vague for a reason, because if I go in the details, it is extremely complicated. The computations are not, it's not very friendly computation. But anyway, the point is that if you, instead of just writing this, if you consider this guy with a particular weight, then the corresponding Feynman-Cat PDE can be solved explicitly. Now this is all good for Brownian motion, where you can really solve the PDE explicitly. Again, that does not really work when you take W to be a semi-multiple, because you cannot really do those explicit computations, because kappa is not a constant. So our new idea in this thing is it suffices to construct super solutions. So you have the PDE. Instead of solving the PDE explicitly, you just construct a super solution of that PDE, and that itself gives you enough information to control this this moment. And from the moment you kind of backtrack, applying this distortion estimate, to control that, and from there, you control this. So this is how we complete the argument. And so it would be in vain, this whole talk would be in vain if I don't give you a theorem, but let me just quickly write a theorem that it says that if kappa, so this kappa S that you see here is away from 8, okay, uniformly, and A is W12 almost surely, then gamma exists, and it is simple if kappa S is less than 4. I cannot handle the equal 4, but so that's it. So this is the theorem which we put. If you have a semi-martingale of that form, which has the bounded variation part, which is finite energy, this really means that 0 to t, a dot square is finite almost surely. And the assumption on kappa S, which is that it is away from 8. In that case, the gamma exists, and it is simple for kappa S, if kappa S is strictly the same. Okay, so I will stop here.